welcome Professor T. Ramchandran, the pioneer of the lecture series. Thank you, sir, for giving us the opportunity to be a part of this. Kindly accept this as a token of our appreciation. A hearty welcome to our chief guest, Dr. Ramachandran, who has joined us today to deliver a lecture on process metallurgy of base metals, successes, challenges, environmental issues, and pathways to solutions. A warm welcome to the Director in Charge and Dean of Faculty Welfare, Professor Kandaswamy. Welcome, sir. A warm welcome to Professor Narayan Prabhu, Head of the Department of Metallurgical and Materials Engineering Department, and all the faculty members, ex-faculty members, students, and staff gathered here. Let us start this lecture by invoking the blessing of the Almighty with a melodious rendition by Shruti.
शरणु सिद्धि विनायका शरणु विद्या प्रदायका शरणु पार्वती तनय मूर्ति शरणु मूषिक वाहना शरणु 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 निटिल नेत्रने देवी सुतने नागभूषण प्रियने निटिल नेत्रने देवी सुतने नागभूषण प्रियने तटिल तांकित कोमलांगने कर्णकुंडल धारने शरणु सिद्धि विनायका शरणु विद्या प्रदायका शरणु पार्वती तनय मूर्ति शरणु मूषिक वाहना शरणु 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 शरणु.
Thank you, Shruti. We now request Professor Narayan Prabhu to address the gathering.
Today's function and Director in Charge of NITK, Professor Kandaswamy. Distinguished Chief Guest of today's function, Dr. V. Ramchandran, Mrs. Vasanti Ramchandran, the former head and founder head of our department and guest of honor, Professor T. Ramchandran, my esteemed colleagues, my former colleagues and gurus, Professor Sudhakar Naik, Professor Prasad Rao, Professor Hebbar, Professor K.L. Bhatt, distinguished alumni, guests, invitees, and my dear students. A very good morning to all of you. My greetings to all of you on the occasion of Karnataka Rajyotsava and Deepavali, the festival of lights. It is my proud privilege to welcome you all to this 23rd lecture under Professor T. Ramchandran Lecture Series. We are all very happy to have with us Dr. Venkoba Ramachandran, an eminent extractive metallurgist from USA, and he is also the backbone behind this lecture series. He was our former member of faculty during 1967 and 69 and a colleague of Professor T. Ramchandran. The very fact that he is coming all the way from US shows his love and affection for Professor T. Ramchandran and our department and NITK. At the outset, I would like to brief you about the genesis of this lecture series, particularly for the benefit of student audience and young faculty. This is the 23rd lecture under Professor TR Lecture Series, which was started in 1991. Professor T. Ramchandran was the founder head of our department. He joined our department as professor and head in the year 1965, and he was mainly responsible for building up of the department and for developing infrastructure and sound base for research. Above all, he has been a good friend and guide to his students and colleagues. During his tenure here, he Also served as principal of KREC and now NITK for 2 years. In 1973, Professor T. Ramchandran was honored by the Department of Metallurgical Engineering of Banaras Hindu University, Varanasi, with the Distinguished Alumnus Award. During 1975-76, 1983-84, and 1990, he was a visiting scientist at the Max Planck Institute for Ferrous Research at Düsseldorf, Germany, from where he obtained his Doctor Engineer degree earlier. He retired in 1989 after 24 years of fruitful service in this institute. The idea of starting this lecture series was originated from his ex-colleagues and students at the time of his retirement. They generously contributed and established a fund to which the funds generated from the national seminar MetMats 89 that was organized by the department to coincide with the superannuation of Professor T. Ramchandran was also added. Last year, thanks to our distinguished alumnus Nagprakash Babu, who donated a sum of $10,000 to sustain this lecture series. The fund is now managed by the institute, and the interest earned from this fund is being utilized in arranging lecture every year by an eminent metallurgist in honor of Professor T. Ramchandran. We are particularly thankful to Dr. V. Ramchandran, our chief guest, who helped us in mobilizing funds for this lecture series by contacting the alumni of our department settled at USA. His selfless efforts have made this lecture series financially self-sustaining. The names of the contributors are printed in the lecture booklet, which will be distributed later. Dr. V. Ramchandran will be shortly delivering a lecture on process metallurgy of base metals, successes, challenges, environmental issues, and pathways to solution. I take this opportunity to introduce our chief guest, Dr. V. Ramchandran. He holds a bachelor's and master's degree in metallurgical engineering from the University of Pune. He obtained his PhD in metallurgical engineering from Colorado School of Mines, Colorado, in United States. He is a professional engineer in the state of Arizona and also a qualified environmental professional. He has about 8 years of work experience in India, including 2 years in our department. He has 26 years of R&D work experience in the area of extractive metallurgy of non-ferrous metals at a major non-ferrous metallurgical industrial laboratory. He is also having 13 years of consulting work to the non-ferrous metal industry with emphasis on industrial wastewater treatment. And he is also a co-author of Extractive Metallurgy of Nickel, Cobalt, and Platinum Group of Metal, published by Elsevier in the year 2011. And today morning, he has donated a copy to our department. He is very active in TMS, the Materials and Society. He was also the chairman of various technical committees. He is the organizer and chairman of technical symposia, editor and co-editor of symposia publication. He has organized and taught technical courses at annual technical meetings. He is the recipient of Milton E. Wadsworth Hydrometallurgy Award in 2001 in recognition of his contributions to the understanding of hydrometallurgical processes and their application for the treatment of process effluents and training. He is also the recipient of TMS 2008 Distinguished Services Award for decades of distinguished service to improve the environmental performance of non-ferrous smelting and refining processes, and to TMS in various capacities. Currently, Dr. V. Ramchandran works as a consulting engineer and resides in Arizona in United States. Association, Department of Metallurgical and Materials Engineering, and National Institute of Technology, Karnataka, I extend a very warm welcome to you, sir. I extend a hearty welcome to Professor T. Ramachandran, our guest of honor. Sir, we are honored by your presence. In a couple of years, this lecture series will be celebrating its silver jubilee. And this coincides with the golden jubilee of our department. We are very keen to celebrate this event in a grand manner, and we look forward to you, sir, for your continued guidance, encouragement, and support. Professor Swapan Bhattacharya, our beloved director, is a patron of our association and is a constant source of inspiration to all of us. He always encourages and supports us in all the activities of our department. Due to some prior commitments, he is unable to attend this program. He has sent his best wishes for the success of this lecture program. Dr. A. Kandaswamy, Dean Faculty Welfare, he is today officiating as a director in charge. He is a professor in the Department of Mathematics. He is a well-wisher of our department and always supports us in all our activities. On behalf of MEA, Department of Metallurgical Materials Engineering, and on my personal behalf, I welcome you, sir, and he has kindly agreed to preside over this function. I once again welcome all of you to this 23rd lecture in Professor T. Ramachandran lecture series. Thank you very much.
Sir, we now request Professor T. Ramachandran to share a few words with us.
Sir Prabhu, members and office bearers of the Metallurgical Engineering Association, ladies and gentlemen. If normally in this, I start by saying that every year I make a pilgrimage to the metallurgy department and then pass on to some problem and then talk about it. I'm not in a position to do so today because I had a fairly rough night traveling by train from Thrissur. So I would talk for a long time, but one or two points I want to make. Almost 46 years ago, I suppose, there was a selection interview for staff to the department. And 2 days before the selection interview, or a few days earlier, I get a letter saying that one of our esteemed applicants writes, "Sir, I'm sorry I can't attend the interview. I'm getting married on that day." And he has enclosed an invitation letter also. So at the board meeting, this was the favorite candidate of ours. We wanted him very much. So I presented it to the board and say that we have to consider him in absentia. Fortunately, the board in those days were a bit lenient and they said, all right, go ahead. And that is how Dr. Ramachandran became a member of the Metallurgical Engineering Department without to go through the rigors of interview and all that. After that, from 67 onwards, if the old records of department are still there, you will see every document which we gave for placing of orders for equipment or whatever, everything was handwritten, mostly by him, partly by me. In those days, getting something typed in the college office, we didn't have an office of our own. You write up the order and then expect them to get it typed and sent. You go to the registrar 15 times and he will say, yes, yes, I will do it immediately, and then it will remain there. So we decided to bypass the registrar by not having to depend on him for typing. We used to make handwritten comparisons of equipment costs and things like that, comparative statement and actual order also, everything handwritten, with a copy we would keep here and one copy we would go give it to the college office. That way most of the orders were placed in those days. So, and from the day one, we got on very well together. He was a great enthusiast for the department. I must say, in to do justice to the other people also, there in those years, between 67 and probably 75, a large number of people came here, joined the department, stayed for 1 or 2 years, but contributed very much more than the time they stayed in the department. Somehow they all were very enthusiastic, whether it is planning laboratories, planning lectures, writing syllabus. So it was a great group effort in those days. And of course, Dr. Ramchandran was one of the key persons in that. Dr. Raghunathan was there. He stayed for 3 years. But all of them, a large number of them stayed. Dr. Parameswaran stayed only for 15 months, but contributed so much. Like that, all those people helped in the initial stages. Otherwise, this department would not have reached this stage. The 10 years, when so many people came, short time, but very actively participated in the building. But normal tendency would be, anyway, I am leaving after. They had all applied and either got admission to foreign universities or were in the process. But they didn't say, anyway, I'll just spend 1 year here and go away. No, they all stayed there and did a lot of work. So that was a great help for me. And if I have been able to achieve anything, it is because of this. Because all these people contributed mightily to that. Well, I don't, if I talk more, I get emotional also. So I'll stop here and say that for all those people who are appearing for the examinations in the next few months, all the best. And to all of you, a happy Diwali. Thank you.
We now request Professor Kandasamy to deliver the presidential address.
Respectful Professor T. Ramachandran and today's chief guest, Professor V. Ramachandran, Mrs. V. Ramachandran, and my respectful professors of Metallurgical Department, Professor Sudhar Naik, Professor Prasad Rao, Professor K.L. Bhatt, Professor Hebbar, and Professor Narayan Prabhu, head of the department, and my dear colleagues and students. I am blessed and honored to be here today to share the dais with a great stalwart like Professor T. Ramachandran. When Professor Prabhu, head of the department, called me, sir, you have to be the president of this function, I was not very comfortable, even though it's a great opportunity, but still I am little shaky or I am not comfortable. The sense, with such a great people, I am sitting here, and great people I am facing in front of me, the professors, even though I am not a student from this institute, but I learnt a lot from the people like Professor Sudhar Naik, Professor Prasad Rao. If at all any good quality I have, I don't know. Definitely I would have got it from these people only. Very dedicated teachers, very dedicated administrators, well-wishers, great. And I was wondering how I am associated with the metallurgy. I mean, by sheer coincidence, today I have to be here. And but otherwise, I was thinking what I can tell a bit about. Probably I have taught even this present batch of BTech students. I can teach for 3-4 hours continuously, no problem. But I cannot. My students are laughing. But I cannot even just give a talk for 5 minutes or something like that. I was wondering what I will talk. Then suddenly I remember, yeah, I also have worked in metallurgy. After completing my PhD in IIT Bombay, I worked in a metallurgical department for 1 year with one Professor Balal, who is very much associated with our Department of Metallurgical and Material Science Engineering. Oh, okay, sorry. Oh, that 1 year only made me to realize or to understand the applications of mathematics. I am basically from mathematics. We talk about analysis, assumptions, approximations, convergence, divergence, etc. Otherwise, we will not bother about where it is being applied in chemical way or metallurgical way or computer way. But when I worked with him, I realized almost 1 year I was working as a research scientist with him in a project. I realized and I was mesmerized how this mathematics, and he is very well knowledgeable mathematics. I cannot talk mathematics with him. Rather, I had to learn mathematics from him, Professor Balal. And I think I remember I worked in a project called ESR, electroslag refining process. I don't know whether it is correct or not, no, I forgot. But electroslag refining process, we applied finite volume method and developed a software. And that was a great learning period for me, I can say. And he only advised, afterwards I was to go abroad, then he advised, if at all you have any idea of coming back and coming to the academic line, think of KREC. That time it was called the Karnataka Regional Engineering College, KREC. So from abroad I applied here, first job. Fortunately I got maybe, and I settled here. Then sometime regarding this materials, as here and there we study something, we read in a paper or article or something. Some time back I remember in a Hindu only, one photo has come into 2050, how the flight will be. It's full of glass, where you can see completely, you can sit and see outside. Nothing will be there to see outside, that is different. But that will happen in 2050. Boeing is already started working in that. That is how it is possible. Without this materials, right? How it is possible? Today, Columbia or Challenger, just like that, it is going and coming back like a flight. There are so many fields. Our students, I used to see sometimes, they used to wear the T-shirt saying that we mold the world. How apt? Yeah, that's true. You are molding the world. How apt? Actually, that's the best probably. I don't know who coined that word, but that is the best. I mean, there are enough. I mean, this is a great area. And without materials, we can't think of anything in life or in this. Otherwise, we would have been in Stone Age only, I think. So there are enough potential to do research in this, and I think such a lecture series, this is a 23rd year. Incidentally, I joined 91, but that year I have not many lecture series I have. I think in our institute only 2 lecture series, Professor T. Ramachandran lecture series and Professor G. Subbarao from chemical department, only 2 lecture series. Such a series of seminar or talks definitely will inspire to do research and to find out a lot of good things which will be helpful for the civilization, humankind. This, I wish everybody a happy Diwali, and I will conclude this. Thank you.
Thank you, sir. We now request Professor Kandasamy to hand over this memento to our chief guest, Dr. V. Ramachandran. V. Ramachandran. Sir, to Professor V. Ramachandran. Yes, sir. Thank you, sir. We now request Professor Narayan Prabhu to present a memento to Professor T. Ramachandran. We request Professor Rajendra Udupa to hand over this memento to Professor Kandasamy. Thank you, sir. Let us now welcome Dr. V. Ramchandran to deliver the lecture on process metallurgy of base metals, successes, challenges, environmental issues, and pathways to solution.
Thank you very much. I'm very happy to be here on this occasion of the 23rd Dr. T.R. lecture series. Professor Kandaswamy, Professor Ramchandran, Professor Prabhu, distinguished guests, alumni, and students. Let me first thank you for the invitation to deliver this lecture. It's a pleasure to be among all the old surroundings and see the extraordinary progress that I have seen in the last, of course, quite a while since I have not been here. I'm here to share my experiences, what I have learned in the extractive metallurgy in the last 25 years, 30 years. And if at all why you wonder why I chose this topic, this is the I know the best in a limited way, okay? Especially the base metals on copper, lead, and zinc. I have also collected some quick information on iron and steel industry, a little bit on aluminum industry, a little bit on titanium industry, in passing magnesium, and then we'll go on to the base metals, copper, lead, and zinc. And the driving force a lot of time has been the environmental issues, and we chat a little bit about it. Basically, what the successes have been in the industry for the last 50 years, what are the challenges facing these industries, and the possible solutions that you as new research engineers would possibly look for, or at least should be the direction look for. The next one, please. So we will go through a brief reference to the process metallurgy of iron and steel, aluminum and titanium, process metallurgy of lead, zinc, and copper. In copper, the topic that I know the best, probably go through pyrometallurgy and hydroelectrometallurgy. The next one, please. Possible value-added products, like what we call the byproducts that come from the extractive metal of these three metals. All the environmental issues associated with these extraction of metals, air, water, and hygiene. Water is a subject dear to my heart, so maybe one or two extra slides on that. Sustainable development, probably a little passing reference. You will keep on hearing this word. How it is going to be evolved, we will find out. Challenges facing the production of base metals, these three we will kind of summarize. And in conclusion, and what the metallurgist prays every night when he goes to bed. In the iron and steel industry, quickly as you can see, the focus is on cost, quality, productivity, and functionality. You will always see that doesn't matter what metallurgy it is, the goal is always to go to a poorer and poorer quality of raw material or fluxes or reducing agents, and still make the same quality of iron and steel. So poor iron ores or low carbon content coke or high ash cokes are all being in the forefront and still make good iron and steel. Productivity is an issue. We have gone from about 1.5 tons per day per cubic meter to 3 tons per day per cubic meter. Very large blast furnaces, as you can see, almost triple, a little more than triple in the volume of the blast furnaces volumes, the corresponding increase in production. Electric furnaces has been the forefront, as not a stopgap, but to handle scrap material, so that relatively recycling of scrap material and things like that can be treated through electric furnaces to produce quality steel. The so-called production of what you call very low residual steel, implying that very low impurities and everything, is also a challenging factor. And also trying to produce what we call directly reduced iron as a feed to the electric furnaces is coming up. The problem with the scraps and everything is more like impurities, and the impurities create what we call a hazardous waste called electric arc furnace dust. And so relatively purer and purer iron input to the electric furnace to produce steel is coming up. I've been looking at this, at least learning about the Corex furnace. I think there's a plant in Karnataka, if I'm not mistaken, and which is a two-step process in order to produce steel from, iron from very low-grade coke, low-grade coals, and low-grade iron ores. At the mines, beneficiation is an issue. High ash coking coals needs to be beneficiated so that you can use them in the blast furnaces. Environmental targets for CO2 is an issue. Off-gas cleaning in sinter plants, particulates removal, SOx removal, NOx removal, they're all gas cleaning systems, they're all challenges. Are expensive, but it has to be done properly. Ultra low residuals like low sulfur, low phosphorus demands from product requirement, making the steel making much more challenging. High energy recovery, always talked about but not easily said or done, is say recovering heat from slags or recovering some heat from the outgoing gases. The next one, please. So these are the kind of summarized value of the challenges facing the iron. So basically productivity, production of the same quality material from low grade materials is the challenge that you'll face, and we'll have to be looking at continually. Alumina, very quickly, the bauxite mining, you make specialty bauxite manufacture, you refine alumina to make alumina metal, and there are specialty aluminas and alumina chemicals. These are the environmental considerations. One or two slides are not in the probably chronological order, but quickly, dust control in mining, dust control in refining, storage and transport. But the main environmental problem in the aluminum industry is what we see at the bottom, the bauxite residue disposal, what we call the red mud. You produce about 2 tons of residue per ton of alumina at that pulp density 40 to 70%. Dust contamination, groundwater contamination, and whenever we store the residue, the structural stability, the residue impairment, all this has to be taken into account. We estimate about 4 billion tons of red mud will be collected and stored by the year 2018. Only option at the moment is impoundment. I'll quickly mention the so-called Orbite process, which I see on the horizon. The process was started to treat low-grade aluminous clay, and the products that you can produce is this metal-grade alumina, of course, which will go to aluminum making, pure hematite as a byproduct, and high-purity silica as a byproduct, and some of the byproducts that you see at the bottom, gallium and scandium oxides, which are impurities normally present in the alumina ore. Again, this will always look like a laundry list, not easily said, then done, okay? They will always claim the process will do this, but there is something that you should always have in mind. I've been told that energy costs are an issue, but it's something that anybody looking at how to take care of the red mud problem should at least look at this or look at the approach of this in some way. So there is a demonstration plant in Canada. They're going up to 5 tons per day, and obviously they're looking for sponsors to do this work. This is the quick flow sheet for the Orbite process. The clay or the red mud, you do a hydrochloric acid leach, just remove the silica, and then you have the metal-rich liquor, aluminum iron, you precipitate aluminum chloride, and you make the high-purity alumina here, and then a thermal process to make a ferric oxide, and then the final processing for rare metal processing. This ferric oxide, hopefully the iron industry will take it if you make it, but it all depends on the levels of impurities in that. This is the Hall Herold process. I will not go into the details of this. What I'm trying to imply is that if we talk about challenges or successes, but this process has been a workhorse for the aluminum industry for more than 100 years. Again, just a summary of the environmental considerations. These are the reduction gases that you normally worry about from the aluminum pots, the gaseous emissions, hydrogen fluoride, carbonyl sulfide, and sulfur dioxide. and the cleaning of the gases emanating from the aluminum pot house in order to keep the atmosphere clean. Spent pot liners have been getting a lot of attention, and because of fluorides in them and everything, anything in that direction as to how to handle them in an environmental acceptable way is worth looking at. Again, some more challenges. Raw material supply and quality, that will be the song of the day. Declining alumina content of the bauxite, impurities in the alumina, impurities in the soda rubber electrodes that we prepare, and the availability of calcium fluoride, which makes the bath. And the environmental consideration about hydrofluoric acid, other emissions, CO2, carbonyl sulfides, against spent liner treatment. Next, please. Titanium, we have the conventional sulfate and the chloride process. I have added on the CTL process. It has caught my attention. One more reason why I'm probably talking a little bit about CTL process is it is being developed by one of my close friends. Okay, so he gets some attention here, and his secretarial staff were helpful in preparing the PowerPoint for me. So I promised them 2 or 3 slides on that. Okay. Next, please. The ilmenite concentrate, depending on the titanium content, this is meant for the processing of alumina, the CTL process to produce the pigment. The sulfate process also produces pigment. Depending on the titanium content, you go to a smelting and to make a slag with 80% titania, which can be made into further processing. Rutile, also you make a titanium product. The chloride process makes the titanium oxide pigment directly. This process that we are going to talk about seems to avoid, it is a chloride process, but the downstream process are a little bit better. Challenges of the chloride process: high cost, material operating cost, chlorination temperatures, disposal of iron bind products. Sulfate process, quality of the product, acid digestion, high temperatures, large iron sulfate to be disposed of, and energy. The CTL process again is for low grade aluminum ilmenite ores. There's a possibility that if you have vanadium and chromium as a byproduct, you can recover them by this process. Low environmental impact, and they claim that they have used known steps. The process flow sheet straightforward. The ore goes through a chloride leach, solid liquid separation, and they use solvent extraction. This is the new step that you see for iron, to regenerate the acid for recycle, and then there is you make from the acid generation the hydrolysis to make the iron oxide product. Again, whether the iron industry will take it or not is the question. Yet solvent extraction of titanium and the precipitation. This is a patented process. Some proprietary steps are involved, and also a vanadium extraction process possible. Chromium is not shown here. So this is something that keeps coming up. If you can electrowin titanium from titanium dioxide or any kind of bath, not easy. The big problem is the high affinity of titanium for carbon, oxygen, nitrogen, and the formation of TiO instead of the metal. A lot of talk about it. Not an easy process, but something if you do it, it's going to be a gold star. Coming to the 3 base metals that I always, at least I think I know about, is major applications of lead acid batteries. All other applications of lead is being phased out. Recycling of lead acid batteries is a critical factor. I don't know what percentage is recycled here, but probably close to 85 to 90% of the batteries produced in the United States are recycled. If you go and get a battery changed in a car, he will take your old battery and say, please pay me $10 to dispose of environmentally acceptable way. This is central collection. This is the most difficult thing. There's an Italian process called the Ingitec process, which has been used for treating lead acid batteries. If you find an alternate for lead acid batteries in your car, I believe lead metal will be history. Okay. So far, we have not come up with a battery that has the deep discharge cycle that we have on the lead acid batteries. So have that in mind. So don't spend too much of time trying to get a fancy process for lead. The future for lead, I think, is bleak, mainly because of the environmental issues. I'll show you why. Hydrometallurgical process, as of today, I have not seen a good one. But the Italian process, the so-called Ingitec process, has come up with a process, but extensively tested, but still not commercial. So basically lead quickly is a very relatively mature technology. In other words, all the successes we have had. Pyrometallurgy, these are the different processes. The cinder blast furnace, the isosmelt is a bath smelting. Kino-Schumann is also a bath smelting. QSET is a Russian process. The imperial smelting process is for bulk concentrates. Autotech flash, not useful, obviously, because lead oxide, lead sulfide all have very high vapor pressures and so not easily handleable from the environmental point of view. Caldo is only for secondary materials. SKS process, you see the number of plants is from China, but it's actually a kind of a mixture of other processes or borrowed from others, I would say. Now here again, we always say, how long does it take to develop a process? This took, I haven't listed it still, but this took a good 20 years to have a process that is workable and you can build a plant. There's one plant in India, Hindustan Zinc. They have put one plant, but the rest are all in China. Electrometallurgy, the Bureau of Mines in the United States tried the fused salt electrolysis. It worked, but not environmentally feasible because the vapor pressure of the chloride salts and everything, and not to mention the cost of the process. Now, lead hardly sells anywhere between 40 cents a pound to $1 a pound. Hydrometallurgy, the Engitech process, is a ferric fluoroborate leach and electrowinning, and you recycle the reagent. One lead company has extensively done a demo plant and everything, but they have not gone to the commercial stage still. Probably economics is an issue. This is out of the various smelting operations, the top submerged lance, which is also known as cyrosmelt, outsmelt, isosmelt, they are all synonymous, is a process that used for lead, is better than the lead smelting, the cinder blast furnace operations, and is extensively used for making lead today. It's again not a single stage process. In spite of the best efforts, you'll make molten lead and lead oxide slag, which will have to be reduced in some other furnace, even another isosmelt also. Okay. The same unit can be used, designed for copper. The Tuticorin smelter by Sterlite uses a isosmelt copper, which will come to that, but it can be used for the lead also. Now this is the next, the QSL continuous oxygen converter. The Q stands for Kino-Schumann Lurgi continuous oxygen reactor. Now this works reasonably well, but if you look at this partition wall here, you have all the concentrates in the smelting zone and then the slag reduction zone. The goal is to claim that this is a continuous process. Okay, you just put the concentrates in, you get the lead on the other side, the slag on the here. The slag reduction zone, or you can separate it separately and then it works better. The critical part is the partition wall. Okay, on both sides you get very high temperatures. The integrity of the wall is an issue, and back mixing is an issue. The reactor design is part of the back reaction. You'll have a lot of back mixing, so the slag ends up with a much amount of entrapped bullion or lead oxide. Okay, but if you take this slag separately and treat it in a blast furnace, in a blast furnace, you can, of course, the process will be a little better. Typical oxygen injection, coal injection for slag reduction. Cominco QSET, the Cominco is from Tech Resources. They have the QSET unit. Whenever you have relatively high levels of zinc in the lead concentrates, this works. This is again an auxiliary feed here. This is the shaft. The bullion is tapped at the bottom. The slag is taken over to the electric furnace over here, where you reduce the slag to get a zinc. The slag contains considerable amount of zinc, so you reduce it, and the zinc oxide vapor that comes over, the zinc that vaporizes here is reoxidized to make a zinc oxide fume taken to the zinc industry. Works reasonably well, and the heat from this is taken up in the radiator boiler. The electric furnace also has a boiler, heat recovery in the usual steps. In other words, in one furnace you make bullion on one side and the slag on the other side. If I remember right, Tech does not reduce the slag to recover further lead. Okay, they discard it. They might have some old blast furnaces, they may be doing it, but I think as of now they don't. The next one, please. The SKS technology again is a Chinese technology. It's a horizontal vessel. In other words, I shouldn't say this. It's probably borrowed from different people and put together over a period of time. The Noranda reactors were used for copper concentrates. So they take a air shrouded, and then the oxygen injection is borrowed. The idea is borrowed from the QSL furnace. The SKS is a synonym for Shui Kushan SKS, and then is rapidly being adopted in China. If you take the slack from this and reduce in separate blast furnace, textbook stuff, you're using a Noranda type of reactor to make lead bullion, and then the slag reduced outside. This is simply a sketch of the thing. As the Noranda smelter, you have the feeding port, you have the lead siphon here and the slag port here, same one unit. And if the lead content of the is too high, take it to a blast furnace and reduce it to make elemental lead and oxygen lances here. Quickly, refining of lead. Lead, unfortunately, is a pretty good solvent. So you'll find that, again, it's a relatively mature technology. The pyrometallurgical refining involves the removal of all these metals. You decauterize first, remove arsenic, antimony, bismuth, debismuthize. Bismuth is a byproduct. Precious metals, dure, lead, silver, platinum, everything. And because the zinc used in the removal of the precious metals, you have to de-zinc the lead. Harris process is the use of sodium hydroxide and sodium nitrate to refine lead. These three steps. These three steps are different, but otherwise it's the same. And then you have the electrolytic process, the best process for refining lead bullion. You use best process when the bismuth content of the lead is way too high. The pyrometallurgical refining becomes very expensive. In other words, so they go to the electrolytic process. There have been advances in using a bipolar technology and treatment of lead, the slimes coming off the lead refining for the treatment to produce bismuth and precious metals and things like that. So the bismuth content will determine whether you go to electrolytic process or a pyrometallurgical process. Nothing new that you can really think of, but environmental plays a big role in treating all these processes. This is the thing, lead means environmental problem. Ambient air quality in the workplace, major concern. High vapor pressure of lead or lead sulfide or lead oxide at the operating temperatures. This is the thing that is going to kill all the lead industry. This is the typographical error. It is 0.15 now. Okay, I think we had 1.5 micrograms per liter. We couldn't meet it, and so we had to shut down some lead smelters and refineries in our company. Non-compliance is possibly the reason why you will see the lead smelters and refining being shut down. After next year, there will not be a single lead smelter in the United States. There's only one zinc plant at the moment, and even that's only copper plants are running in the United States. They sort of capture very textbook stuff, acid plant. The tail gas is not scrubbed, so the capture is only 90%. But still the tail gas should meet the SO2 limits, which is 650 parts per million. Zinc, again, relatively mature technology. Pyrometallurgy is the imperial smelting furnace. This is the hydrometallurgy. As we all know, thermodynamics doesn't allow you to get zinc as a vapor because of the reoxidation in the typical blast furnaces. So the imperial smelting is used only for mixed bulk concentrates where you have lead also. Environmentally, it's a nightmare to run imperial smelting furnaces, so they are also being faded away. But if you come across a bulk concentrate where you can make money, then people still use it. Hydrometallurgy, you roast the zinc ore, leach, purification, electrowinning, pressure leach. Instead of roast leach, you can go to skip the roasting operation, go to a pressure leach and autoclave purification. The only environmental problem is the disposal of the iron residue, because iron is always associated with zinc. The jarosite is a byproduct, is fixed as jarofix. Goethite, hematite, all byproducts Everybody will claim that this can be sold to an iron industry. Not a pound has been sold to the iron industry because the iron industry does not want to touch this. If you go to a pressure leach operation, the sulfur in the zinc sulfide concentrates comes out as elemental sulfur, which is separated from the iron residue. Again, not a single buyer for this sulfur. Okay. Purification elute solutions, very textbook stuff. Use of activators. We have gone away from arsenic trioxide because the environmental use is an activator. Optimizing zinc dust usage. Fluidized bed removal for as you know, zinc you cannot electrowin thermodynamically because the delta is not minus NFE, but very small over voltage of hydrogen we call it. There's a narrow window voltage where you can deposit zinc. So the electrolyte has got to be extremely pure, and all the time and money is spent on this. Jumbo cells, polymer concretes, larger size electrodes, wireless monitoring, higher current densities, improvement electrolytes. Secondary materials, low-grade oxide silicates. Only one plant in South Africa or Namibia called the Scorpion Zinc plant. They use silicate ores, but they go through solvent extraction as a must when you use low-grade ores. Next one, please. Challenges: fine grinding and direct leach, not successful so far. Aqueous oxidation sulfides are not easy. That's why we've gone to the. In other words, pressure leaching is possible, but not atmospheric. Bioleaching has been attempted, not very successful. You can continue to look at it. All of them will need this thing. Electrowinning. This should catch somebody's attention here. The electrowinning reduction of cell voltage. I will summarize it when we come through. Some work can be done if you reduce the anode voltage. You will reduce the total cell voltage. You will save a lot of energy. DAC has been tried. The new electrowinning anodes are PGM coated titanium mesh anodes. Some drop in cell voltage, but not enough to justify the cost. Next one, please. Copper. If you have a copper ore, the arrows are not the best, but you can concentrate the ore to make and smelt and electro-refine and cathode, or you can leach the concentrate and go to SX-EW in cathode. And of course, if you have the bio-leaching, heap leaching and all those things, a very low-grade ore, it's either an oxide ore or a low-grade sulfide ore, then you can leach, go to solvent extraction and electro-refine cathode. This again, you talk about great success. This is the solvent extraction is the one that made leaching of low-grade ores possible. Okay, if you did not have a solvent extraction to selectively get copper or solution, the bottom one might not have worked that well. Okay, next please. Again, relatively mature technology. Here is one you have pyro, hydro. In electrometallurgy, you have electro-refining. If you go to a pyrometallurgical process, you make an anode electro-refine. If you go to the hydro, you electro-win directly. Smelting, converting blister, smelting, flash smelting, Autotech flash smelting, Inco flash smelting, Contop smelting, Autotech to blister. Next one, please. So, flash smelting, batch smelting. These have been the two workhorses for the production of copper. And you have batch smelting, reverse furnaces. Nobody uses them anymore. Electric furnace, isosmelt and outsmelt. We talked about it. Mitsubishi is the Japanese bath smelting furnace. Submerged fuel, Noranda, Teniente, they're all Teniente is South American, Noranda is Canadian, Venico is Russian, all submerged fuel smelting. Not too many units in that case. Typical picture of a flash unit. This again is the workhorse. This is the Inco flash smelter. So I have a picture of the Inco. As you can see, you have the feed and the oxygen. The burners are all here. Then you tap mat and the slag. The slag has a discard and the mat goes to converting. The next one, please. This is a picture of the Autotech smelting. If you look at this, the ore, this is the flash smelting unit. They have waste treated boiler. This is the flash smelting unit. The critical factor of this is the single burner on the top of the roof that smelts all the concentrates. Okay, it takes care of everything. You make a mat. You can choose whatever mat grade you want. Flash converting. What they do is in this particular company, they granulate the mat so that all environmental problems are you don't take molten matte back and forth. And go flash converting, you make blister, and then the blister goes to the anode furnace, and then the copper refinery, and then SO2. This environment is a very acceptable process in view of the amount of SO2 that put out, or the sulfur that you put out in terms of per ton of copper. Okay. The next one, please. This is a typical what I call a low emission. It is another form of the previous flow sheet that was pictorial, and you have the flash smelting, granulation, flash converting, and anode refining. Next one, please. Olympic Dam, I just showed, it is the same flash smelting furnace, a little better picture probably, and this is the flash smelting, this is the furnace. The only difference between this is a high grade copper ore, so you make blister directly and there is no converter here, as you can see. Okay? You are able to make blister and that can go directly to the anode furnace. The converter is eliminated completely. Only 3 plants in the whole world run with this process because of the uniqueness of the raw material. How uniqueness of a material raw feed can determine the process that you have. Okay? Next one, please. Converting, textbook stuff again, copper matte, Pierce Smith converter has been the workhorse for 100 years. A couple of other types, Hoboken converter, Autotech flash converter that I talked about, 1 unit, submerged to your Noranda. These are all modifications of various types. Other developments, Codelco looking at some continuous converting, Ausmelt looking at continuous converting, ISA converters using top submerged lance for converting. Here is one place where you can have something to do, how to make continuously copper. You feed concentrated one furnace, smelt it, the matte gets out, you discard the slag, the matte goes to the converter now, okay? The converter, this is where your knowledge should come in to make it continuous converting, okay? Because converter, as you know, has a slag step and a blister step. If you can have a reactor where you can do the slag step and tap the white metal to the second converter and make blister from that, there is something to be looked at, okay? Or do something different or better. So a continuous process for chalcopyrite concentrates is something all these people claim they do, but they don't, okay? They always do it in different ways. Now this is again the batch smelting for the copper. We talked about flash. This is the bath one. This is the isosmelt furnace. The slag rotary holding furnaces, you can reduce the slag a little bit further with coal, and they have a boiler if you want, gas cleaning system, and then the matte goes to converter. The plant in Tuticorin has got an isosmelt furnace. If you look at the Birla thing, I think has 2 or 3 different types of things. I don't know really, but they have 2 or 3 units. One is maybe an house melt, one might be a flash melt. Okay? Hydrometallurgy quickly, leaching, oxide ores, low-grade sulfide ores, heap leaching, solvent extraction of the pregnant leach solution followed by EW is pretty common. Leaching of the concentrate. Now here is one process that I followed recently. Considerable time or money was spent, and the plant built a plant. The plant did not make it after the demo plant. Okay, so how you test it, and once you make a concentrate, you're going to look at: am I going to smelt, make an anode and refine, or concentrate, leach, SXEW? Which is the cheaper way? Okay, one plant in Africa is doing it, but they do it only if they have to. Otherwise, they sell the concentrates. Can be looked at if it is economical. If you avoid solvent extraction or try to save money, it's over. It's not going to work. If you don't grind it well enough, it's over. The process is not economic. Okay, so you're always competing in smelting. Again, it is site specific, ore body specific. You do it if you have a very, say, a small ore body, very good, but 100 miles, 200 miles, 300 miles from reality. So instead of making concentrate and shipping it, you make either anode and ship it or cathode and ship it. The next one, please. Bacterial leaching of copper ores is definitely on the radar screen. I have a friend, she works in this area, she's an expert, and a couple of slides are borrowed or given to me by her, so the credit goes to her. None of these slides are mine. as you can look at these things, depending on the copper grade or the type of ore, you decide what type of leach you go to. Okay, this should be your kind of yardstick or a map. Okay, most of these things work well. The direct leach is not working that well because the grade is high. Still, the heap leach works better than what I call vast leach. Where you have stir tank reactors, very expensive. Concentrate bio leach. This area is where you have claim to fame, okay? Especially if you have secondary sulfides, you can go to a bacterial leach. It's primary sulfide resources, and this, if somebody is doing work in the area of bacterial leaching, is something to look at, okay? The next one, please. As you can see, this leach is very textbook. If you have, if you know methodology, the boronite and chalcocite type of ores leach quite well. The chalcopyrite is the one that does not leach well. This is pretty commercial at the moment. The concentrated bioleach has been typed Biocorp and Backhawks. Backhawks by South Africa, Biocorp by Billiton and Kudelco. They went ahead with a big demo plan, but they have not built a commercial plan to date. Okay. So, the next one, please. This is the dissolution of the mineral, which tells you which is the least easiest to leach. And as you can see, chalcopyrite is next to molybdite, probably the most difficult to leach. Chalcocite and covellite do very easily, even boronite. Arsenopyrite does also, and pyrite also. So in other words, if you have pyrites associated with chalcopyrite, that has to leach first. And the next one, please. What is the problems with chalcopyrite? I have left a copy of this presentation, Dr. Prabhu. So if you really want to seriously go and start looking into this, this is what look, this slide is going to be important. Okay, why chalcopyrite is resistant to dissolution, and why it gets pacified. What are the reasons why it gets pacified? What is the theories involved in it? And look at these things and see whether you can come up with some solutions. Okay, something to look at. The redox potential that you need and everything. How do you reach about 20% will reach in the ambient conditions. Then passivation, temperatures has to be higher. And then from the galvanic series, you have to decide how to go. This is the temperature, what they call thermophiles is one is being developed. If you can develop bacteria in this that can do it, then there's a potential for leaching chalcopyrite. Of course, as you can see, it will take quite a bit of time to do that, but still it could be worth it. In other words, if you do this, you don't have to make a copper concentrate, you don't have to smelt, you simply have to bioleach copper chalcopyrite, SXCW and copper, okay? I keep on saying SXCW and copper. SX is important because the electro 1 copper, the quality was as good as the electro refined copper, and that is the only reason why the SXCW has come into the fore. Electromanagement of copper, this is a laundry list, typically very relatively mature industry, low energy, emphasis on quality. Permanent steel stainless steel cathodes, standard technology, they are industry standard. Automatic machines, robotic handling. Reagent additions, reagent measurements for controlling the smoothness of the copper cathodes and increasing the or maintaining the current efficiency. Cell voltage monitoring and temperature using wireless technology, high current density. These are all coming up. Polymer concrete cells, usual standard technology. Electrowinning, that is where I talked about reducing some energy, and quality is important. Acid mist is important, and that's why the precious metal coated titanium mesh anodes is coming into the fore in copper electrowinning also. In probably all electrowinning, zinc, copper, nickel, they started looking into this. Acid mist reduction, cross ventilation, air sparging. But these are all again in the this is for electrowinning. This is the PGM coated mesh that is giving the cell reduction voltage. These three are important. If you change the alternative anode reaction to decrease the cell voltage, doesn't matter what it is. People add methanol, oxidation of methanol becomes CO2 and water, that reduces, but there are issues involved, but this is some area where something can be done. Value-added products, just a list of the byproducts from the copper circuit, the zinc, lead in general. Basically, technology for sourcing. If you can make a byproduct, you make a byproduct. Otherwise, it becomes a what you call a discard product. Okay. The next one, please. Environmental issues, the awareness is one of the most dramatic drivers. Air, SO2, volatile, heavy metals, particulates, sulfur dioxide has decreased, the sulfur capture has increased. This is the goal, 99.9, which is the equivalent of putting 3.5 kilograms of sulfur out per ton. Acid plant scrubbing is quite tail gas is critical. If you scrub it, you can go below 100 ppm. The limit is 650 ppm. Next one, please. This is one place where if you convert sulfur dioxide to sulfur and not make acid, you got a claim to fame again. We ran a pilot plant for years and years, not very successful. Reactor design was a problem and things like that. None of these things have been commercial. Fugitive emissions, heavy metals. This is coming into the forefront, particularly more. Cleaning up. Whenever you clean air, you'll pollute the water, and you have to clean the water. So water is an important resources. So if you want to use it as a raw material, the best water you use in the most important need, and then the hierarchy will determine where you use it, reuse it, recycle, recycle, reuse, 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 reuse. One company, BHP, is spending $3 billion to desalinate seawater and pump it 14,000 feet altitude and miles to get a feed water supply to copper concentrate. So that tells you how important water it is. Okay? I'm just trying to emphasize the importance. Hygiene, working hygiene is important. Ambient air quality, lead is the bad one. Ambient air quality is 0.15. This 1.5 is creating such a problem that even copper plants are finding it difficult to meet this particular limit at the moment. Okay. Sustainable development is just a usual slide we make. Development that meets the need of the present without compromising ability of future generations to meet their own needs. Basically, is it sustainable? The answer is probably no, in spite of the what we call an oxymoron that sustainability and mining doesn't go together. This is the final conclusion. Incorporation of sustainability consideration by all mining companies in all aspects is a prescription for viable and vibrant mining. Just remember this, if it cannot be grown, you have to mine it. So whether you like it or not, you're going to be mining, okay? Challenges facing the processes, okay? Smelting. Large size plants justify expenditure. If you're building a copper plant, you can nowhere build less than $300,000 for economics. Lead and zinc can get by with a little less. Slag cleaning, important in order to get more metal out of the mine smelter. Produce matte for shipment and converting. In other words, instead of shipping concentrate, ship matte. Goal of a single stage smelting and converting for copper is a question. Hydrometallurgy has not been a good competitor to smelting for copper except for bioleaching low grade ores. Electrometallurgy, energy saving by reduction of voltage. This is another challenge, you shortage of university educated manpower for and basically not too many people are going to metallurgy, as TR always says it in his comments. The next one, please. What are the drivers for new technologies? Reduce production cost, management, reduce capital cost, improved quality. This is one thing, the management is going to say, this is the ore I have, these are the impurities. You make good copper for me. So how do you handle the impurities? You have to look at. Reduce energy, type of energy, the usual arguments, and these three environmental issues. So what do I have to say in conclusion? If I can find my cards. golden age of process metallurgy is probably coming to an end. In other words, you are not going to jump out of the water and say eureka and say I have a process. Okay, nobody has $1 million process in an afternoon. Okay, let us remind that. Flash smelting, 25 years. Batch smelting, 20 years. Chinese process I told you, 20 years. Okay, none of them has been done. The pressure metallurgy for zinc, 15, 20 years. Okay, so it's kind of coming to an end. Evolutionary improvements will continue by incremental improvements. Breakthrough technologies will be implemented on a site-by-site basis where local conditions favor business case. In other words, it may be if you have a very typical ore, okay, and it cannot be done by conventional methods, and so you may want to look at it. For example, the driver in that case may be, it's a very bad ore. It's a copper ore with all kinds of arsenic, antimony bad, but it's got a lot of gold and silver, okay, then that will be the driving force for you to go for it, okay. Energy needs will go increase as the ore grade decrease. Decrease in ore grade will increase energy, just a number there. Poorer, more impure ore grades will demand sophisticated process steps to produce metal of acceptable quality. Impurities, either a byproduct or a discard. Now, any metallurgist who goes to bed, he says, please grant that I may take into my system only acceptable